Hello students, good evening. Welcome to another video of Vedantu Karnataka. This is Catherine, your physics master teacher. Quickly, can you let me know if I am audible and visible? How are you all doing? Are you all enjoying your Sunday? Let me also check. I think I'm live. Just a second. Hi Daniel. Hello. Welcome to the session. Where is everybody else? Quickly, all of you send the link to all your friends. Today we're going to do the last part of the next chapter, electrostatic potential and capacitance. Okay. Hi Priya. Hi RXBTCC. How are you all doing? How was your weekend? All of you doing well? Just a second. Let me also verify on. Give me 1 second, students. I'm good. How are you? Are you also doing well? So did you all start preparing for your unit test? Did you get your dates? When is physics? Regions have different dates. So let me know when your dates are. When your physics exam is. Good evening, Priya. How are you? How are you doing? Sorry. Are you also doing well? So did you all start preparing for your unit test? Did you get your dates? Okay, so shall we start with today's lesson? Yes, my live chat is ready here. Okay. So as you saw on the thumbnail, today we are going to do electrostatics itself. We already did part 1, so today we're going to do part 2. Are you all ready? Yes, Priya. Hi. Are you all ready for the lesson? Quickly, let me know in the chat. If you're ready, put some fire emojis in the chat. Yes. I am audible, right? I believe I am audible. Okay, I'm ready. So let's begin. Yes, ma'am, ready. Okay. I am also ready. You're also ready. Let's start. So last class we discussed about what is electric potential energy, potential difference, and all of that. Okay. So today we are going to start with some derivations, very important derivations. So first we will look at the derivations for electric potential due to a dipole along the axial position, equatorial position, and general position. Okay. So last class we looked at what is electric potential difference and all that. Okay, if you've not watched that, quickly after the live, you should quickly go watch that. If you're watching this recorded, please watch that and then watch this. It's part 1, this is part 2. Okay, yeah. Okay, so let's start. So we're going to start with electric potential due to a dipole along the axial position. Now, what does an axial position mean? Axial position means along the straight line. See, what is a dipole, students? You've been learning dipole since first chapter. What is a dipole? Two opposite charges, one plus charge, one negative charge, which is placed at a distance. It is a dipole, right? Now, if you have a dipole, and you want to find out the electric potential at an axial position, which is along the same line. What do you do? That is what we are going to see here. So first thing, let's make a dipole. So to make a dipole, what do I need? I need a negative charge and a positive charge. Two charges. See, a dipole is when you have two equal and opposite charges, and if they're separated by a distance. So let's say they're separated by a distance 2l. Okay. So if they're separated by a distance 2l, then we can say if this is the midpoint, then this much is L, this is also L. Okay? Yes? Okay? So the whole thing is 2L. Now I am going to find out the electric potential at a point P along the same line of the dipole. That is the meaning of axial. Axial means along the same line of the dipole. Yes. Okay. Now I will say that P is at a distance r from the center of the dipole. What does that mean? If this is the center of the dipole, okay? From the center of the dipole, P is at a distance of r. Okay, so what is r? R is the distance from the point P. The point P is where you need to find out the electric potential. From the point P all the way till the center of the dipole. Yes, it's written here. The electric field at point P on the axial line is at a distance r from O. O is the center of the dipole. Now let's do the easy derivation. Easy derivation. Okay. So first thing, the potential at point P will be the potential due to both the charges. It will be the potential due to the charge plus Q plus the potential due to the charge minus Q. Both of them contribute to the potential at point P. You all agree with that? Yes? So let's do that. Now what is the formula for potential? Yesterday we looked at that. K into Q by R. Right, general formula for potential is 1 by 4 pi epsilon naught Q divided by, if the distance is R, you put R. So this is the same as KQ by R. Yes, this we've discussed. So here, let us look at what the distance will be and we will write down the formula for potential because of plus Q and potential because of minus Q. Now potential because of plus Q. So where is plus Q? This is plus Q, this is point P. So you can see plus Q and P. What is the distance? Till here, this much is R and this much. How do I do that? So this much is what you have to find out. I mean, this much is, no. Okay, oh yeah, I can do that. So this is the distance that we need. Okay, the distance between plus Q to point P. That is the distance that we need. How will I find out that distance? I know R is this much, L is this much. So R minus L will give me that green part. Won't it give it to me? Yes. So the potential will be K, 1 by 4 pi epsilon naught. I'll write it as K. The charge is plus Q, so I put it as Q divided by, what is the distance? R minus L plus, here K, the charge is minus Q divided by, what is the distance? So if I am to take the distance from minus Q all the way till P is this much. So that will be, this is P, this is minus Q. This much is R, this much is L. So won't it be R plus L? Yes, you understand that? So won't it be R plus L? Is that much clear? Now let's do some math. So KQ is common, I'll take it outside. KQ, I take it outside. What remains? R minus L plus 1 by R plus L. Okay. Now what will that be? That will be KQ outside. KQ outside. I take the LCM. So R plus L minus R minus L in brackets, the whole divided by R minus L into R plus L is A minus B into A plus B is A square minus B square. So R square minus L square. Now this is equal to R minus R will cancel. L minus minus L will be 2L. So KQ 2L, the whole divided by R square minus L square is VP. Okay, is VP. Okay, I'll answer your doubts in 1 second. Let me just finish this so I don't break the flow of the derivation. All right. Yes. So VP is equal to KQ2L R square minus L square. Now I'm going to teach you a new term which I've already taught in last chapter. But once again I'll teach you for those who are attending from this lesson. Now a new term called dipole moment. Okay. So dipole moment gives you how the dipole moves. The dipole always moves from negative to positive. And dipole moment is given by P. Okay. So the alphabet for dipole moment is P. P is equal to Q, which is the charge, into the length of the dipole. Okay. So this is the general formula. The general formula of a dipole moment P is whatever charge is there into the distance between the two charges. So here the distance between the two charges is 2L. So it's Q into 2L. Now if the distance between the two charges is X, it will be Q into X. Okay. So 2L is not a constant value. It is the distance between whatever the distance between the two dipoles is, that will be your 2L. Instead of 2L, you should put that. So now VP will be what? VP will be K into Q12, I will put it as P, KP divided by R square minus L square. Okay? Alright. Now, one more thing I can do is if it's a very short dipole. Okay? So imagine the two charges are placed very close together. So 2L is a very small value. The charges are very close and it's a very short dipole. Then I can say that 12 is very small compared to R, isn't it? So you can ignore L square and write down the formula as Vp is equal to Kp by R square. Okay. So you can say Vp is equal, okay, let me write that down for a very short dipole. For a short dipole. For a short dipole, that means R is very big compared to L. The distance between the dipole is very small. So what happens? R square minus L square can approximately be written as R square itself. Isn't it? R square minus L square can approximately be written as R square itself. So in that case, we can modify this equation and write Vp as Kp divided by R square. Okay, this can also be written as 1 by 4 pi epsilon naught. K is 1 by 4 pi epsilon naught. P divided by R square. From this, it is clear that the potential is proportional to 1 by R square. Okay. So what is the formula for electric dipole, potential due to axial position? What is the formula? It is Kp by R square. Let's put a big box on it. Okay. Yes. So this is a very easy derivation. Alright. Now let's look at the doubts. Anime fan, ma'am, why minus in the numerator? Okay, that is, I just put minus to show you that is the potential because of the minus charge. That minus is not needed there. Okay. When you're doing the math, you don't put the minus. Okay. I just put minus there to show you that is the term for minus. This is the term for plus. You don't have to put that. It's okay. All right. You are only looking at magnitude here. No directions. So there's no negative sign here. It doesn't matter. Atharva, weightage of this chapter, this has a very high weightage. Atharva, all the first 3 chapters, very high weightage. They're the most important chapters. Okay. So is this much clear to you? This is the derivation for electric field due to axial position. Okay. Is my live chat not working? Is this clear to all of you? 1 second. I think my chat is stuck. Yes. Okay. So I hope this is clear. Now let's look at the next part. Next part where we are going to find out thank you anime fan. We are going to do the same derivation for which part? Okay, let's do a question. I think question we should do. Point P. No, let's do equatorial. Okay. Next is the electric field due to a dipole because of the equatorial position. So these are two very, commonly asked questions. The same could be asked for electric field as well. From this chapter, these are two commonly asked questions. So electric field due to a dipole on an equatorial position. What does equatorial mean? Again, you have a dipole, but this time you're going to take a point P above it. Previous time you took a point P on its side. This time you're going to take a point P above it. Okay. So let's draw the dipole. Let's put a negative Q charge here. A positive Q charge here. Okay. And I'll take a point P here. So I'm going to find out the electric potential due to the dipoles point P. Okay, due to these two dipoles at point P. Perfect. Now here also, what is the distance between the two dipoles? The distance between the two dipoles is 12. Okay, and point P is at a distance r from the center. Same thing we did last time. Last time also point P was at a distance r from the center. Here also point P is at a distance r from the center O. So how much would each of these be? So this will be L. This will also be L. So how find out this? Pythagoras theorem. Square root of r square plus L square. This is also square root of r square plus L square. How did I get that? Some of you are wondering how I got that. Say basic math. Okay, this side is r, this side is L. So hypotenuse square is equal to side square plus side square. So hypotenuse is equal to square root of side square plus side square. This is what I've done. Okay. Yeah. Thank you, Mahi. Please tell all your friends there's a teacher like this and ask them to come watch the videos and subscribe to the channel. Okay. Yeah. Okay. So this is the basic figure. Figures are very important. When you do these two derivations, please make sure you draw the figure. I hope the figure is clear to all of you. So this much is L and this is also L. The whole thing is 2L. Okay? Hi Rakshita. So let's do the derivation. Very easy derivation. So total potential at point P will be the potential because of plus Q plus the potential because of minus Q. Okay? Potential because of plus Q, potential because of minus Q. Just a second. Oh, one small mistake I made here. I had to. Yeah, here it is plus. Here it is negative. Okay. So anime fan, yes. I thought you were talking about why you put minus Q as minus Q. Minus Q is because of the charge. It's because of the charge negative and I have to take it outside. I did it right here, but I put it out there. Sorry, my bad. Okay? Yeah. Thank you, anime fan, for pointing that out. Okay? Is this clear? Yes. Yes. Please let me know if this is clear. So minus Q, I take it outside. That's how I subtract. Okay, that's how that's how I did the whole thing. Okay, let's move on to this. So this is V plus VQ plus V minus Q. So now this is what? VQ is what? K. K times charge times the distance between the charge to point P. Here what is the distance? The distance is square root of R square plus L square plus K into minus Q. The whole divided by the distance is R square plus L square. Okay. Now what does this become? KQ divided by square root of R square plus L square minus KQ divided by square root of R square plus L square. Now what is this going to be equal to? This is going to be equal to 0, isn't it? It's the same term. So when you subtract them, it will be 0. So the electric potential due to a dipole along the axial position, or sometimes it's called broadside on position, but it's usually equatorial position. Okay. So the electric potential due to a dipole of the equatorial position is always 0. Okay. Electric potential due to a dipole along the axial position is always equal to Kp by R square or whatever distance Kp by R square, but along the axial position it is 0. Okay. Yes. None of you have liked the video. Please like the video. Quickly like the video. It's just one like. Come on, students. Where is all your energy? Quickly like the video. No. Our physics army will feel bad. Question. What is the work done in moving a test charge Q through a distance of 1 centimeter along the equatorial axis of an electric dipole? You can all pause the video and quickly do it. Okay. Not to those who are watching live, to those who are watching recorded. So those who are watching live, can you tell me know what the answer is? See. So I have minus Q plus Q. I have a dipole. Okay. And I have a charge Q which is at an equatorial position through a distance of 1 centimeter. Okay, this is 1 centimeter. Hi Dylan, this is 1 centimeter. So the charge Q is at a distance of 1 centimeter. So what is the electric potential? Without doing any step, I can say electric potential is 0 because it's equatorial. But let me do steps also. So I can say that the work done in moving the charge is basically Q times the change in potential. Yes, Dylan, 0. Very good, very good. Okay, very good, Dylan. So it's Q times change in potential. So here it is Q times V, let's say VB minus VA. Okay, if the potential because of minus Q and minus A, I subtract it. Now what is VB minus VA? 0. So Q into 0 is 0. Very good, Sanant. Very good, Sanant Revankar. Superb. So directly you can put 0 because you know at equatorial position the potential is 0. So potential into charge is work done. So it's obviously 0. Very good, very good. You all make me so proud. Superb. So next question. Next question, the third derivation for electric potential due to dipole. So we looked at the axial one, we looked at the equatorial one. Now we look at a general one. So some of you might be wondering, ma'am, general position and all derivation they don't ask, but you will get numericals based on this. Okay, derivations they may ask, but usually they ask axial or equatorial. But this formula is very important. The formula for general position, you will need them to do numericals. Okay, so it's important that you understand the concept. So for general position, again, we need to have two dipoles, minus Q plus Q. Okay, and they are at a distance of 2L as always. Now let's take a point P. Okay, let's take a point P which is at a random position. It is not along the axial position. It's not along the equatorial position. It is at a random position. And let's say I am putting this point P at an angle theta. So as always, the distance between point P to the center is R. General things that we always do. Okay, there's a dipole. I take a point P, not along the axial position, nor the equatorial position. I take it at a random position, which makes an angle theta with the dipole. Okay, things that we already do. So we also know that the formula for potential is usually potential of charge Q plus potential of charge minus Q. Okay. Now what I'm going to do is, I'm going to take two lines. Okay. I'm going to draw lines joining the two charges to the point P. Okay. So minus Q to P and plus Q to P. Let me just call this R1 and R2. Okay, so R1 is the line joining plus Q to P, R2 is the line joining minus Q to P. Now let's do the math. What is VQ going to be equal to? Obviously K into Q divided by what? Divided by R1 plus K into minus Q divided by R2. So now this is equal to KQ 1 by R1 minus 1 by 2. Now this is equal to KQ, I will cross multiply R2 minus R1 by R1 R2. So now I have my formula. VP is equal to KQ R2 minus R1 R2 minus R1 divided by R1 Now let's do the rest. Okay, is this much clear to all of you? Yes. So for a short dipole, yes, we will come to that. Now, all my smart students are already giving me the final answer. Now, for a short dipole, what happens? For a short dipole, what should I do? I should take uh obviously R2 minus R. Okay, for a short dipole, what should I do? Yeah, that is what you are all answering. Which color? Let me take orange. Okay. So, what is the difference between R2 and R1? So, if I draw a line like this, okay, I think I should take black. Yeah. If I draw a line like this, okay, I draw a black line like that, then don't you think this much will be R2 minus R1? Isn't it? See, if this is R1 and this is R2, R2 is longer by a small portion. So that longer portion will be R2 minus R1. The rest of the portion, both R1 and R2 have the same length. But after some portion, it is longer. R2 is longer by R1. So R2 minus R1 is that length. Now, if I take this angle as theta, okay, this is obviously 90 degree. Yeah, this is 90 degree. This is 90 degree. So now what does this form? This forms a triangle like this. This forms a triangle like this. Yes. So what I can do, as anime fan and as Dylan says, I will take cos theta. Okay. So I can take the cos theta element. So R2 minus R1 will be what? This side. This is 2L. This is R2 minus R1. And yeah, this side I have to find out. So this is the hypotenuse. Okay, this is the hypotenuse. Hypotenuse is always the side opposite the 90-degree angle. So whichever side is opposite 90-degree angle, that is a hypotenuse. So if this is theta, what do I do? Cos theta will be adjacent side by hypotenuse. So what is the adjacent side? R2 minus R1 is the adjacent side by hypotenuse is 2L. So from this I will get R2 minus R1 is equal to cos theta into 2L. Okay? Yes? Sanath? Is this not clear to you, Sanath? Yes, no. Which part is not clear to you? Can you tell me? Is it the figure? So what I did is, I just drew a line on R2, making it the same length as R1. So I will draw it with a scale if you want it more neat. So this time I have actually drawn all the lines earlier itself, so I don't waste time. So if I draw a line like this, okay. So if I draw a line like this, you will see that the part of R2 after that line is basically R2 minus R1, and this angle is 90 degree. So you just take the triangle. So, okay, let me shade the triangle. So you just take this whole triangle. Okay. So you take this triangle, and how R2 minus R1 is your doubt? Okay, that is very easy. Okay. How R2 minus R1? Let's see. See, if you have, let's say you have two straight lines. Okay. Let's say you have two straight lines. All right. This is R2. This is R1. All right, Sanath. So Sanath has a doubt on how that is R2 minus R1. Let's say you have two straight lines. This is R2 and this is R1. If I draw a line like this, what will this part be? Won't it be? Okay, let's name it. Let's name this R2 and this R1 so you're not confused. Okay. So this line, won't it be R2 minus R1? Because that's the extra length. Do you get that? So same thing I've done here. So they both come together. So till a particular point, they have the same length. But after that, R2 goes even further. So that extra length is basically R2 minus R1. Okay. Is that clear? Sanat? I hope that's clear. If it's not clear, you can let me know. I'll explain it again. Okay, I don't mind explaining 100 times. The only point is you should understand. So now you understand how I get cos theta. I'm going to erase that. If you want to, note that down, quickly take a screenshot. I'm going to erase that. Yeah. Okay. So now, what do we have? So we have R2 minus R1 is equal to 2L cos theta. R2 minus R1 is 2L cos theta. So, if it's a very short, Lakshmi, why we should take cos theta instead of sin theta? I'll tell you, okay? So, the general formulas, we write them all in terms of cos theta. So, you will see in this chapter, whatever formulas we do, we'll write them all in terms of cos theta. Okay, now why I can explain it to you. So, if you have an x-axis and a y-axis, let's say there's a force of 10 Newton. Okay, let's say there's a force of 10 Newton acting. And let's say it's acting at an angle theta. So then the horizontal component is 10 cos theta. Vertical component is 10 sin theta. So which one acts to the dipole here? So you can see the dipole is along this part. So there is no point in taking vertical component, isn't it? Because our point P has effects because of the dipole. So the dipole is along the horizontal axis. The horizontal axis is the x-axis, which is cos theta. Okay. Dhanraj, tell ma'am. What should I tell? I didn't understand. Okay. Is this clear? Clear? Cool. Okay. Okay. Okay, so now I have R2 minus R1 is 2L cos theta. So R2, let's say R2 is approximately equal to R1. We already saw that. There's only a small difference, R2 minus R1, small term, but otherwise R2 and R1 are approximately the same. So this is approximately equal to R. Okay. So this is approximately equal to R. So can I say R1 into R2 is approximately equal to R square? Yes. So if R2 is approximately equal to R1, R1 into R2 is approximately equal to R square. So now what will my VP be? VP will be K into Q into, what is my formula? Instead of R2 minus R1, I will write 2L cos theta. Okay. Instead of R2 minus R1, I write 2L cos theta. The whole divided by, instead of R1 into R2, I will write R square. Superb. Now this Q2L is what? The new term that you learned, dipole moment. So K into 2QL becomes P. So Kp cos theta by R square. The one and only equation for general position. Okay, let's put it in a box. Successfully. Okay. Is this clear to all of you? So this is the formula for electric potential due to dipole at any general point. Okay, so this P can be anywhere. Wherever the P is, you can use this formula. So now, see, you will understand where to use this when we look at questions. Okay. So then it will be very clear on how to use this. Let me just look at that. Okay. Now imagine you have point P at an angle where theta is. You don't know the formula for equatorial and axial. Okay. So I give you a question. Find out the electric potential due to a dipole at a point where theta is 0. So when theta is 0, obviously it means axial position. Now because you are all smart, you know the formula for axial position, so you will directly tell me. But imagine someone does not know axial position. What will they do? They can take the formula for general position and put Kp as cos 0 divided by r square. What is cos 0? 1. So you get Kp by r square, which is the formula we derived first today. Yes? Okay. Now I'm giving you another question. So, ma'am, yeah, let's say you find out the electric potential due to a dipole when it's at 90 degrees. So when it's at 90 degrees, if they ask you to find out, what will you do? You will put theta is 90 and you will get cos 90 is 0. So Vp is equal to 0. But you are a smart kid. You already know electric potential due to equatorial is 0. So you know it's 0, but those who don't know that and know only the general position formula, they can do it this way. Yeah, 180 also you can do. 0, whatever angle you want, you can do. Let's say this is my dipole and I want to take a point P here. It's at an angle 80 or 120 or 160. Wherever you want, you can find out the electric potential using this formula. Yes? Is this clear? Dhanraj, Lakshmi? Yes, Dylan, very good. In that case, it's -1. You're all very attentive today. Kudos, kudos. Very good, very good. Super. Okay? Let's move on. Okay. Next is the electric potential due to a system of charges. Okay, now we are super smart. We know at different positions. But now what happens if there are so many charges? So let's say this is point P. Okay, this is point P and I have so many charges. Q1, Q2, Q3, Q4. You know how many other charges I have, I can put. But Q5, that much is enough. Okay, I don't want to waste time writing so many charges. Some random number of charges are there. Okay, and they are all at a distance of R1, R2, R3, R4, R5 with respect to P. I want to find out the total potential. So obviously it will be potential because of 1 plus potential because of 2 plus potential because of 3 till potential because of n. Okay. Yes. So then Vp will be, what is potential because of 1? K times Q1 by R1 plus K times Q2 by R2 all the way till K times Qn by Rn. So this is the formula for electric potential due to n charges. N can be any value. So this also, they will not ask you the derivation. They will not ask you derive a formula or anything. They will just give you a system with 5 charges and ask you to find out. Okay. So these are all cases where you need only formulas. Nothing else is required. Okay. Yes, Dylan. Very good. You're adding them. Okay. Let's do a question where things like these are going to be used. So some of you are wondering, what is ma'am teaching? So let's apply what I'm teaching. Okay. Yeah. 2 charged spheres. Okay. One has a radii of 5 centimeter. The other has a radii of 10 centimeter. So it should be technically big. And they are connected by a thin wire. No current will flow between them if they have the same charge on the sphere. They have same electric potential, same electrostatic energy, same surface area. Which one? Which one? All my smart bachas. Quickly tell me the answer. So one thing that you should know is the charged spheres will have the same potential. Yes. Yes, they have the same potential. VA is equal to VB. So what will delta V be? Delta V will be 0. So if delta V is 0, then what is the answer? Same potential. Option B. Yes, Dylan. Yes, Dhanraj. Yes, yes. Very good, very good. They have the same potential. Because if they have the same potential, then current need not flow. Then their current does not have to flow. When does current flow? When there is a potential difference. Yes. Superb. Okay, we'll do one more question. 27 drops of the same size 27 drops of the same size are each charged to 220 volts. Okay, so there are 27 drops like this. They are of all of the same size and they all have a charge of 220 volts. And they together will form a big drop. We have to calculate the potential of the big drop. That is the question. Okay, let's do that. Quickly, all of you do that. I will also do it. So, see, obviously, the initial potential should be equal to the final potential, isn't it? How many ever drops are there? The total initial potential should be equal to the final potential. So, initial potential is what? 27 small drops. So, 27 into 4 by 3 pi, I'll put small r cube. So, this should be equal to, okay, before that, the volume should also be the same. So, initial volume should be equal to the final volume, not the potential volume. Okay. So, initially, you have 27 drops. So, all of those 27 drops together should give you a big drop. Both these should have the same volume, isn't it? The volume of all 27 drops together should be equal to the volume of the big drop. So, volume of the big drop, I'll take it as 4 by 3 pi. I'll take big R cube. So 4 by 3 pi cancels. 27 r cube is equal to capital R into cube. So r cube cancels. I mean, they don't cancel. I take the cube root. So what does this become? So the cube root of 27 will be 3r will be r. I get this. Okay. Now let's apply that in our question. So we know that potential is what? Potential is kq by r and we know the total potential is 220. So this is the same as k into 27 times the charges, the whole divided by, in that case, the radius will be 3r. Okay. So this will be 220. Yes. So the potential of k q by r. What is q here? Q is the charge and here our charge is 27q and here our distance is 3r. So 27q by 3r. So 27 and 3 cancels. So let's put this as 9. So 9kq by r will be 220 volts. Okay. 220 volts. One second. Swalpa Kannada, I'm really sorry dear. Swalpa Kannada, I will try. Okay. See. So this is now equal to what? I put equal to 220 here, but that's not there. Okay. So the potential, the total potential V is equal to 220. Okay. Which is KQ by R. Now, R potential is what? V prime, which is K into what is the charge? 27Q, distance is 3R. So, this becomes 9KQ by R. So, this KQ by R is how much? That is the potential. It is 220. So, this is basically 9 into 220, which is 1980 volts. Okay? Yes, Dylan, you're right. You're right. Okay. So, Paru, we have two more physics teachers. They'll be teaching in Kannada and English mix. Okay. Because we have got a lot of requests from students asking for Kannada. Okay. Is this fine to all of you? So, 27 drops are there. They're all of the same size and each of them have a charge of 220. So, the charge of one is KQ by R is 220. So, I will just substitute that here. Okay. So this here will be volume. I think that is clear. 9kq by r is 220. Yes. Okay. Let's move on. Okay, there's one more question. So these kinds of questions are very commonly asked questions. Okay, this is a very important 5 marker. I've seen such questions in lots of papers. So, two charges. Okay, I have to. Two charges plus 3 into 10 raised to minus 8 coulombs and minus 2 into 10 raised to minus 8 coulombs are placed 15 centimeters apart. Okay. So, this is one charge 3 into 10 raised to minus 8 coulomb. This is another charge minus 2 into 10 raised to minus 8 coulombs. Okay. And they are placed 15 centimeter apart. Okay. Yes. At what point on the line joining them is the electric potential 0? So at some point, let's say, let me just put a random point. Let's say at this point, okay, at this point, the electric potential is 0. I'm assuming, okay, but the actual point I have to find out. Okay, so I'm assuming that it's that point. So with respect to that point, now I need to write down the coordinates. Okay, so this full thing is 15 centimeter. Now with respect to that point, what I will do, I will take this much as 15 minus x and this much as x. Do you all agree? Yes? You all like how I took it? If you want to take it the other way around, you can take it that way also. This is easier. Okay, smaller part you take it as 15 minus x, the rest is x. Now let's do math, simple math. So, okay, Dhanraj is quick. He already got 9 centimeter. Let's see. So the total potential is V of plus Q plus V of minus Q. So this is KQ divided by, what is the distance with respect to the positive charge? We are taking it with respect to point P. Okay. So from point P, how much is it till the positive charge? X plus. From point P, how much is it to the negative charge? 15 minus x. So this is K minus Q divided by 15 minus x. Okay, this is Q1 and Q2. They're not the same. Okay. Q1 and Q2. Okay. So initially I had to take P2 plus Q, then P2 minus Q. Okay. Now let's do again the rest of the math. K and K will cancel. Q1 and Q2 will be there. Okay. So K and K will cancel. Let's write down the values of Q1 and Q2. Q1 is 3 into 10 raised to minus 8 divided by x minus Q2 is 2 into 10 raised to 8 divided by 15 minus x. Now we know that at point P the potential is 0. How do I know that? It's there in the question. That is the question. Find out a point on the line where the potential is 0. So now I take one of this to the other side. So what does this become? Minus 2 into 10 raised to minus 8. I take it to the other side. So this will become plus 2 into 10 raised to minus 8. The whole divided by 15 minus x will be equal to 3 into 10 raised to minus 8 by x. Where did the negative term go? I just took it to the other side. So 10 raised to minus 8, 10 raised to minus 8 I can cancel. Now what remains? 3 by x is equal to 2 divided by 15 minus x. Yes. Now I can cross multiply. 3 into 15 minus x is what? 3 into 15 is 45 minus 3x is equal to 2x. Now x I take to the other side. 45 is equal to minus x. No, not minus x. It will be plus, no? Minus 3x goes to the other side. This becomes plus 5x. So x will be 45 by 5, which is 9 centimeters. So our Dhanraj was right. It is 9 centimeters. So from minus 2 into 10 raised to minus 8, if you go 9 centimeters, you will get a point. No, if you go 15 minus 9 centimeters, you will get a point where the potential is 0. Okay. So it is at 9 centimeters from here and 15 minus 9 from here. Okay. But one common mistake that students do is they stop here. This is not the end. There is one more part to this. So that is the most tricky part of this. Now I can ask you, why can't point P be outside the line? Why can't point P be here or in front? It need not be in the center. In the question, it does not say in the center or on the line. It just says along the line. Okay, so for most of the exams, all of students, what they do is they stop here. But this is a 5 marker, so you shouldn't stop here. So you should take one more case. Okay, so what is the second case? The second case, everything else is the same. You have 3 into 10 raised to minus 8 here. You have minus 2 into 10 raised to minus 8 here. The whole thing is 15 centimeters. Okay. But in this case, what you're going to do is you're going to take a point P outside the line. Okay. So point P is, so this distance is now X. Alright. So now you take point P at a distance X after the charge. It could be on this side also. You can put it on this side also. I'm just taking it on one side. Okay. So you have to do it on one side. Where are you going then, Raj? What about the rest of the class? We discussed capacitance and all of that. Okay. So X can be taken on any side. So what will the formula be here? Same thing. Vp is equal to Vq plus Vq minus. And this is going to be 0. So this is basically K into Q1 divided by first distance is this. So it will be 15 plus X. Okay. 15 plus X and then this much. Okay. Let me write that down. So 3 into 10 raised to minus 8 is at a distance along the whole green line. So this is 15 plus X till point P, right? Minus KQ2, the whole divide. Okay, here I'll put equal to, because anyways I'm going to take it to the other side. Equal to KQ2 divided by just X. Okay. Okay. So K and K cancels. Q1 and Q2 I'll put values. Quickly let me finish it. So 3 into 10 raised to minus 8 divided by 15 plus X is equal to 2 into 10 raised to minus 8 divided by X. Now minus 8 cancel. Same procedure. 3X is equal to 15 into 2 is 30 plus 2X, 5X by 30. Okay, this will go to the other side. 3 minus 2 is 1X. So X will be 30 centimeter. Okay. So the charges can be placed either at 9 centimeter or at 30 centimeter. Yes, Dantraj, it's 30 centimeter. Hi Sharmila, welcome to the class. Okay. So students, all of you quickly send this link to all your friends. Let them also join. It's an amazing session, right? Yeah. Big ma'am, you are only saying your session is amazing. What is this? Huh? Okay. Now I have one more question here which you will do as homework. Okay. This is a homework question, and in the chats, in the comments, please let me know the answers. I can give you a quick hint here. What you have to do is you have to find out V axial. So for V axial, what will your formula be? It will be Kp by R square. K is given, P is given, R square is given. V equatorial, you don't have to do anything. You know what the value is. I'm not going to tell you. You know what the value is. If you know the derivation, you know what the value is. And then V general. See, for questions like this, find out the electric potential on a line making an angle of 60 degree with the dipole axis. That's when you take V general. So Kp cos theta by R square. So theta you have to take it as 60. Okay. So please comment the answer. All these are 5 markers. Alright. Sanand, this is also a 5 mark question. Okay. So comment the answer after class. Do it and let me know in the comments. I'll be reading all your comments. I'll reply to your comments. Okay. If you have the correct answers. Alright. Next, let's look at the derivation for electric potential due to a uniformly charged thin spherical shell. Okay. So we have a spherical shell which has lots of charges, full of charges everywhere. Okay, we have a shell that's full of charges. Let's say the shell has a radius of r. Okay, now electric field inside a shell is 0. If you don't know how, watch the videos of first chapter. Okay, so electric field inside a shell is always 0. All right, now what we're going to do is we're going to find out the electric potential. Our question here is electric potential. So first thing, let's take an outer point. Okay, let's take an outer point. Okay, let's assume the outer point P. Okay, let's take a random outer point P. At P, the electric field will be how much? The electric field will be 1 by 4 pi epsilon naught Q divided by R square. Okay, so R square is the distance till P. And we also know this we learned in last class, part 1. Electric field can be represented as the negative gradient of dV by dr. Remember this? We did it in the last class. So now, can I write V as minus integral EdR? Yes, this also I've discussed in the last class. So what did I do? I took dr to the other side and integral of dv is v. Those who have doubts in integration, I have explained the integration in part 1 of this video. Part 1 of electrostatic potential. Okay, you can go watch that. Yeah, so v is equal to minus of integral E dr. Okay, now let's do it. Now let's do the integration. So v is equal to minus of integral. What is the electric field? 1 by 4 pi epsilon naught Q by R square into dr. Now I have to put limits. Okay, so what will my limits be? So the minimum I can go is infinity and the maximum I can go is till the boundary. Boundary is at R. Okay, so infinity till R. Now this is equal to, I take the constants outside, so minus Q divided by 4 pi epsilon naught integral infinity to R dr by R square. So this integration, how to do it, last video, you can just check it out. Okay, so integral of 1 by R square is minus 1 by R. So this is going to be equal to minus Q by 4 pi epsilon naught minus 1 by R, and then I have to apply the limits. Okay, I have to apply the limits. So this is going to be equal to minus minus, I take it outside, it becomes plus. Q divided by 4 pi epsilon naught, for 1 by R, first I substitute it as R, minus 1 by infinity. It's always upper limit minus lower limit. All this I have explained in detail in part 1 of this class. Okay, so minus 1 by infinity goes, it's cancelled. So this becomes Q by 4 pi epsilon naught R. Now 1 by 4 pi epsilon naught, I write it as K. So this becomes KQ by R. So from this, potential is KQ by R and potential is proportional to 1 by R. Okay. So where at an outer point. So if P is outside, then the potential is proportional to 1 by R. Okay. Now, if B is what? If you are taking a point at the surface. Okay. So if you're taking a point at the surface, what happens? Then R will be equal to R. Yes. So why did I take small r here? Because I had to go all the way till a point P outside. So if it's the surface, then R is equal to R. Okay. So Vs is equal to KQ by, instead of small r, I can put capital letter R. Okay. And this will be a constant. Okay. And this will be a constant. Why would it be a constant? Because all the values are constant. K is a constant, Q is a constant, R is a constant. It's not going to change. In the first part, outside, you can take any point. Depending on where you take, the distance will change. Here, nothing will change, so it's going to be a constant. Now, I can take one more case, which is part C. Okay, what is part C? At a point inside, okay, I think I can write it. Okay, let me write it here itself. At a point inside, can you see? Is my head covering it? At a point inside, what happens? What is electric field inside? 0. Inside, electric field is 0. So, let me put that here. Yeah. So, at a point inside, what happens? Inside the sphere, we know from chapter 1, electric field is 0. Now, what is the relationship? Electric field is equal to minus dV by dr. So, 0 is equal to minus dV by dr. Now, when you differentiate something, if you are getting 0, that means what you are differentiating is a constant. So, this also in part 1 we've learned d by dt of a constant is 0. So, from this we know that V is a constant. Okay? Why? Because whenever you differentiate constants, you should get 0. Okay? So now I have all the 3 cases. Yes, I have 3 cases. What are the 3 cases? Where my first case is the electric potential due to a surface when the electric potential at an outermost point, and then I have electric potential due to a charged spherical shell at the surface, and then I have it at a point inside. Okay? Is all 3 clear to all of you at these 3 cases? Okay. Sanad, you're directly watching part 2. That's okay. Okay. If you know integration and differentiation, you can directly watch part 2. There's no problem. Okay. But, in part 1, I've discussed on what is potential and all those concepts. If you're clear with that, you can directly watch part 2. But otherwise, it's good if you can watch that as well. Okay. Now, I will do a graph for this. Okay. Let me draw a graph for this. So, the graph I've already drawn because, So, to draw the graph, I'm going to take the 3 different positions. So, I know outside V is proportional to 1 by R. Inside, V is a constant. Sorry, on the surface, V is a constant. And inside, V is 0. Okay? Inside, V is 0. So, if I draw the graph, what happens? If I draw a graph, what happens? So, if this is R, okay? If this is R, till this point, initially V is a constant and then V is proportional to 1 by R. So, this is the part on the surface and then this is the part outside. Inside is 0. I'm not representing that here. Okay? Now, what does this mean? This means that, so here, imagine there's a lot of potential, okay? And all these potentials are, 10 volts, 10 volts, 10 volts. As you move, it keeps on decreasing. Okay? So that is what this means. Is this clear to all of you? The graph and the derivation? Okay, Sanand. Hi, Manyasri. Hi, Prajwal. You are from 10th class. So you want to top your class? Are you here to learn advanced topics? Yes? Welcome, Prajwal from 10th class. So if you have friends in 11th class and 12th class, tell them to learn from Vedantu, Karnataka. And we are coming for you also. 10th class videos will start soon. Okay, next question. This similar question we've done, but yeah, let's do it. A hollow metal sphere, okay, it has a radius of 5 centimeter. It is charged such that the potential on the surface is now 10 volts. Find the potential at the center of the sphere. Okay. So what will the potential at the center of the sphere be? This same thing, we have to use this formula. Okay. At the center of the sphere, potential is a constant. So if the potential outside is 10, the potential at the center will also be 10 because it's a constant. Do you understand that? Yes? So outside if it's 10, inside also it will be 10 because potential on the surface is a constant. At the center also it's a constant. If you put it at a point P, then it's continuously decreasing. If I take this point, then it will be continuously decreasing. But everywhere else, it will be 10 volts. Electric field inside is 0, but potential is constant. Okay? Clear? Can I have a fire emoji in the chat if this is clear to all of you? Did you all like the video? How many likes do I have? It's just one like that I see. Please students, please like the video so we can keep giving you wonderful comment. You know, that's how you support your teachers. Liking, sharing, subscribing, sharing to all your friends. Okay. Next is equipotential surface. So we're done with electric dipole. Next topic, equipotential surface. Then we look at capacitance and then khatam, chapter done. All set to go for your exam. Okay, quickly in 1 hour we'll finish this chapter. So equipotential surface, what is equipotential surface? It is any surface that has the same potential at any point. Okay, so wherever you go, you should have the same potential. Yeah, I have a figure. Okay, so if I have, let's say I have a charge Q. Okay, let's say I have a charge Q. It's a point charge, okay? Let's say I have a charge Q, okay? Now, if I draw a shell around the charge such that at any point on the shell, the potential is kq by r. What is kq by r? V, okay? At any point I take, the potential is kq by r. So because of the charge Q, along the surface, it has the same potential. Now if I take another ring, it will have, let's say, kq by r2. The full ring will have potential kq by r2. So such surface is called, so this distance is r. Now if I take another ring at a distance r2, it will have kq by r2. Okay. So any surface that has the same electrical potential at every point is called an equipotential surface. Okay. Now, if you join all the points which have the same potential, you will get the equipotential surface. So, in very simple terms, equipotential surface is a surface where electrical potential is same throughout. Okay? This is the definition. Any surface that has same electrical potential at every point on it is called an equipotential surface. Okay? Now we look at the properties of equipotential surface. It's very important. The properties of equipotential surface. Come on. Yeah, pen. What is the first property? No work is done in moving a test charge over an equipotential surface. Why? What is the formula for work done? Work done is Q delta V. This formula I have clearly explained in part 1. So, on an equipotential surface, the potential is the same everywhere. So, the difference in potential, delta V is Q2 minus Q1 or Q1 minus Q2, the difference in potential. If these two potentials are same, difference in potential is 0. So, work done is 0. Okay. Yes. So delta V will be 0 because it is an equipotential surface. 0. Okay. Hi Shilpa. Yes, Dhanraj. Dhanraj is back. Next, the electric field line is always perpendicular to the equipotential surface at every point. I put this figure for you to just understand that. So if you look at this figure, wherever I take the electric field and the equipotential surface, see, they are at 90 degrees. See, So the ring is the equipotential surface and the blue lines are the field lines from the positive charge. All of you know, from positive field lines move out. And the ring is the equipotential surface. So you can see every time the equipotential surface and the electric field, they are all at 90 degrees. Okay. Next point. Electric potential surface are closer together in regions of strong electric field and further apart in regions of weak electric field. Same thing. Say if you have a positive charge, field is stronger near the charge. As you go away from the field, field is weaker. So look at the equipotential surface. So if you look at this, here the gap between the two charges, the two surfaces, it's less. But see here you have such a big gap. But here you have a small gap. Small gap. Bigger, bigger, bigger. It keeps on becoming the gap between the two surfaces. It keeps on getting bigger and bigger as you move away from the charge. So the equipotential surface near the charge is stronger. And as you move away from the charge, it gets bigger and bigger and bigger. The distance between two lines, you can see the distance between two circles. It just gets bigger and bigger. That is all that is meant here. Okay, did you understand all the properties? What they mean? Yes. Next one, no two equipotential surfaces can intersect or interact with each other. Obviously, do you see one sphere interacting with another sphere? Okay, I can show you a proof for that. Imagine there is one equipotential surface here, another equipotential surface here. So let's say this is 5 volts. Okay, so every point should be 5. Every point should be 5. Okay, an equipotential surface means it should have the same potential. And this surface is 10 volts. Okay, so every point should be 10. But is that practically possible? If you look at this point from this circle it has 5, from this circle it has 10. So it is not the same. So that is not an equipotential surface because there's 5 and 10. That is not possible. An equipotential surface should have only one value of voltage or one value of potential. So if they intersect, then they will have a different value of potential, which is not possible. Okay? Yes. Are we sorted? Hello, cute Sanjay. Is it fine? Okay. Let's move on. Next, what we're going to discuss is we're going to discuss dipoles. Okay, here what we're going to look at is the work done in rotating a dipole. Okay, are you very cute, Sanjay? Sanjay has named himself Cute Sanjay. Cute. Hi, Lava, you're late to the class. Okay. So, first thing, let's take an electric field. Okay, so this is an electric field. All these straight lines, they represent electric field. And I'll put two charges here. So let this charge be plus Q. Let this charge be minus Q. Okay. Let this charge be plus Q. Let this charge be minus Q. And the distance between the dipole, let's say it is 2L. Alright. Distance is 2L. Now, in the electric field, plus Q will experience a force QE. Minus Q will experience a force QE in the opposite direction. Okay. Plus Q and minus Q, they will experience a force QE in two different directions. Now let's say the dipole. What is dipole? Two equal and opposite charges. So the electric field is like this, the dipole is like this. So let's say the dipole is at an angle theta with respect to the electric field. Okay. So this is the direction of electric field. Dipole is like this. This is electric field. So it makes an angle theta with the electric field. Then using trigonometry, if this is theta, how will I find this side? This side will be, obviously this is the opposite side. So I should take sine theta. So sine theta will be this side by 2L. So rearranging, this side will be 2L sine theta. Okay. Is this much clear to all of you? Figure clear? So now, let's say, let the dipole be rotated by an angle. Okay. let the dipole be rotated by some random angle. Let's say the angle is d theta. And I am going to find out the work done, which is dW. dW is equal to torque into d theta. This you've learned in first PU. Okay. So why am I taking d theta? Why am I taking dW? Because I'm taking the angle I'm taking a small angle. Okay. So what I have to do is I have to find out the work done for that small amount of work done. 1 second, students. Yeah. So I'm taking a small angle d theta. So I'm taking small amount of work done. Yes, I have to integrate. Very good. Who's that? Neat. Heart. You love neat. Very good. Very good. Oh, YG Lava has exam. All the best for your exam, dear. Do well. So now I will integrate. So the minimum work done is 0. Maximum work done can be W. So this will be equal to integral of torque. The minimum angle, let's say it's theta 1. Maximum is theta 2. Before that, what is torque? Torque is equal to PE sine theta. This is one formula that we already have learned. You can watch the previous videos to check how. Torque is PE sine theta. Yes. So let's put PE here. So here this will become PE sine theta d theta. Okay. PE sine theta d theta. Now let's do the integration. So integral of dW is W. And when I apply the limits, what will it become? W minus 0 will be equal to PE is a constant. So I take PE outside. Integral of sine theta is what? Minus cos theta. Theta 2 to theta 1. Now those of you who have doubts in integration, you can watch part 1 where I have explained the integration part. So W will be equal to PE. I put the negative sign outside. So this becomes cos theta 1 minus cos theta 2. Okay. So now what you will get? Work done is equal to PE. Sorry, this is theta 2, right? Upper limit minus lower limit. So this will be cos theta 2 minus cos theta 1. Upper limit minus lower limit. Theta 1. So when I multiply the negative sign inside, I can write this as cos theta 1 minus cos theta 2. So this is the formula for work done. Where is my box? Let me put a box. Okay. Okay. Yes. Yes. Very good. Neat. Very good. Manyasri. Very good. All of you. Okay. So work done. This is the formula to find out the work done in rotation of a dipole. So what is a dipole? Two charges. The dipole is kept at an angle here. Okay. And the amount of work done is given by this formula. Now, how do we use it for problems? So if theta 1 is 90 degrees, okay, then what is the work done? Work done will be PE cos 90 minus cos theta 2. This will be PE minus cos theta 2 minus PE cos theta. Theta 2, I'll just put it as theta. So like this, at different angles, you can find out the work done. Okay. But here, our main aim is not to find out work done. Our main aim is to find out potential energy and things like that. So let's look at that. Okay. Is this much clear? From this, what we can find out? From this, Is this much clear? Yeah. Okay. So now from this, I will find out the potential energy of a dipole. Okay. So I'll find out the potential energy of a dipole in a uniform electric field. How do I do that? I write down the formula for work done. So work done is what? Minus PE cos theta. When theta is 90, work done is minus PE cos theta. So whenever there is work done, it is stored as potential energy. So potential energy is also equal to minus PE cos theta. So from this you can say that potential energy is equal to minus P dot E. Okay? It is equal to minus P dot E. Now how did I get that? If initially the dipole is perpendicular to the direction of the electric field. So what does that mean? That means that this is the electric field and initially the dipole is like this. Okay? Initially this is plus Q minus Q. Initially the dipole is perpendicular to the electric field. That means theta 1 is 90. Then it is rotated with potential energy U, which is given by minus P dot E. Is this clear to all of you? Okay. If initially the dipole is 90 degree, then it is rotated by this much to give you potential energy minus P dot E. Now we can consider two cases. Okay. We can consider two cases. So the first case is when theta is equal to 0 degree. Okay. So when theta is equal to 0 degree, what happens to potential energy? Potential energy is minimum, which means this is stable equilibrium. Now when theta is 180 degree, potential energy is maximum and this is unstable equilibrium. I can give you a simple example for you to understand that. Imagine you have a cone, some shape, okay? If you put a ball here or here, wherever you put the ball, it will always come back here, which is the value of minimum potential energy. It will always come back, right? If it's a curved path, wherever you put the ball, it will always come to the bottom. So that is the most stable position where the potential energy is minimum. Now, if you take a surface like this and keep a ball here, potential energy is the maximum there, but it's always unstable there. Okay? So these are the two conditions for stable equilibrium and unstable equilibrium. Stable equilibrium is when the potential energy is minimum, like, when it's at rest. Okay? Where it is minus PE, angle is theta. Unstable equilibrium is when potential energy is maximum. Now, with respect to electric field also, I can explain it to you. So, if this is your electric field, okay. So, this is the direction of electric field and let's say this is minus Q, this is plus Q. So, dipole always moves from minus Q to plus Q. So, the dipole moment will be P. So, P and E are in the same direction. So, that is when it is stable equilibrium. Okay. Now, the same thing, what happens in unstable equilibrium? So, this is the electric field. But in this case, what happens to the dipole? It will be in the opposite direction. So, this is minus Q and this is plus Q. So, it is in the opposite direction. So, dipole moment, as I said, always from negative to positive. So, this is the direction of dipole moment and this is the direction of electric field. So, they are in opposite directions. So, that is when it is anti-stable equilibrium and the angle between them is 180. Isn't it? If this is P and this is E, the angle between them is 180 degree. Okay? Yes. Next is when there is zero potential. When does it have zero potential? If this is the electric field and this is the dipole, okay, and the angle between them is 90 degree, then it has zero potential. Because cos 90 is what? Cos 90 is 0. Okay? Yes, neat, you are right. When angle 0, potential maximum. Topper monkey, I got 667 rank in KCET because of you teachers. Thank you so much, Topper monkey. All of these comments mean a lot to us. Okay? And thank you for coming and letting us know all this in the live. So then we have a lot of students. We have proof that we can teach well in KCET and students like these are proof. Topper monkey, please comment under the videos also, not just in the live chat, so other students can also see. Okay? And they trust us. Okay. Question. An electric dipole consists of charge plus Q and minus Q separated by a distance L. Okay. So this is charge plus Q. This is charge minus Q. And let's say it is separated by a distance L. If the dipole is in stable equilibrium in a uniform electric field E, what is the electrostatic potential energy of the dipole in this position? It's very easy. So dipole moment is what? P is equal to Q times the distance. So here the distance is L. So Q times L. Now U is what? Minus PE cos theta, which is the potential energy. So P is what? Minus Q into L E cos theta. Here what is cos theta? Here the angle is 0, isn't it? Angle is 0. So minus QL E. Very easy question. Thank you so much, topper. Your name itself says topper. Okay? Yes. So they're placed in a uniform electric field. Okay. So that is why theta is 0. Electric field, dipole, same direction. Okay. Let's now start with capacitance. Okay. So we finished potential, we finished dipole, all that is done. Last topic for the day, electrical capacitance. Okay. So we're going to look at electrical capacitance. So before we look at electrical capacitance, let me tell you what electrical capacitance is. So if you have a conductor which has a lot of charges, okay, a conductor with a lot of charges on the surface, what is a potential? It is kq by r. Okay, if the radius of the conductor is r, kq by r. From this, it's very clear that potential is directly proportional to the charge, right? Q is directly proportional to, so I can say Q is directly proportional to V. If V is proportional to Q, Q is proportional to V. This much I can do from things that you already know. Now what I'm going to do is a very simple thing. I'm going to remove the proportionality by putting an equal to and a constant. So in my classes I've always been saying whenever you have to remove proportionality, what should you put? You should put an equal to and a constant. This is the rule. So here what I will put an equal to and my constant I'll put C with respect to V. So this is the formula for capacitance. So from this, what is capacitance? Q by V. Simple. If you know the potential for voltage or potential, you can write down the formula for capacitance. So capacitance is Q by V. It is a scalar quantity. Okay. It is a scalar quantity. And what will its unit be? Q is charge, which is coulomb, divided by V is volt. So coulomb by volt. It can be also written as farad. Okay. Yes, neat. It is a device used to store charge. Very good. If this much is clear, this is the basics of capacitance. Okay. So this is what I have written, I have typed out here as well. So same thing I have typed out here. Okay. So Q is proportional to V. So Q is equal to CV. C is equal to Q by V. Now in Q is proportional to V, how did I get? From V is equal to KQ by R. Okay. Now in simple terms, it is what? It is the amount of charge required to increase the potential of the conductor by 1 unit. Okay. So if C is equal to Q by V, it means that capacitance is the amount of charge required to increase the potential of the conductor by 1 unit. Okay. Done. Electrical capacitance of a conductor is clear. Let's move on to the next topic. Hi Bharati Natikar. Welcome to the class. I hope you're all enjoying the class because I enjoy teaching all of you. So much fun. Next, we're going to look at capacitance of an isolated spherical conductor. Okay. Capacitance of an isolated spherical conductor. So I've typed out the derivation here, but let's do it. Alright, let's do it. So what I'm going to do is, I'm going to write down the potential at the surface of a conductor. So what is the potential at the surface of a conductor? V is equal to 1 by 4 pi epsilon 0. If the charge is Q, and let's say the distance is R. Okay, so this is a different diagram. So let's say the distance is R. Okay. Okay? Yeah. So now what I'm going to do? I know that C is equal to V by Q. So what I will do? I should divide this V also by Q. So 1 by 4 pi epsilon naught Q by R. Uh, Sorry, other way around. Q by V. You should correct me, no? C is equal to Q by V. So this is Q divided by 1 by 4 pi epsilon naught Q by R. So obviously Q and Q cancels. 1 by 4 pi will go up. So C will be 4 pi epsilon naught R. Okay? Let me write this neatly. So those of you have watched my previous classes, they know I'm a very messy. I write in a way. I write as a mess. So now I have started a new mission to write neatly on the board, and I think I'm doing okay. I'm proud of myself. So yeah. So Q they cancel. So you will get C is equal to 4 pi epsilon naught R. Okay. So from this, it's very clear that C is proportional to R, and 4 pi epsilon naught is how much? 1 by 9 into 10 raised to 9. Okay. Is this clear? Now, if the same capacitor is in a medium, okay, if the capacitor is in a medium, so if it is in any medium, okay, if it's in any medium, then it will have a new value of capacitance, which is going to be equal to 4 pi epsilon r. So epsilon naught is for free space, epsilon is when it is in a medium. So this is basically equal to 4 pi epsilon naught into k. Okay, epsilon naught is for free space, k is the constant for the medium. So epsilon is epsilon naught k. So I can write C dash is equal to 4 pi epsilon naught r is what? C. So I can write it as C into K, where K is the dielectric constant. So I have so many terms here. Let me put boxes for all of them. Box, 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 box. So first box here, Control C, Control V. Yeah. Oh my God, what did I just do? What did I just do? Undo. Okay. So now, hey. Sorry, students. This is not my fault. The board is misbehaving. Undo. Yeah. I'm really sorry. Yeah. It's to write on these boards, it's not as easy as it looks, okay? It needs skill, which I don't have. Hey, come on. Okay. Uh, Go, go, go. No. I don't know what's happening. This is happening for me. This is happening for the first time. Okay, done. Okay. Yeah. Very good. Okay. So these are the three formulas for capacitance. First is the capacitance for a normal conductor. Then if the conductor is in a medium, this is how the capacitance will change. Oh my God, NEET, you have already found out the value of capacitance. So NEET says the capacitance of Earth is 711 microfarad from this formula. Okay. So you should find this out, and if NEET is correct, put it in the chat. Okay. Put it in the comments. What is the capacitance of Earth? Naveen, hello Naveen, welcome to the lesson. What's your age? You look like our senior. Obviously, I am your senior. I should be elder than you, right? Only if I have passed my first PU, I can teach you. So I'm like your senior. Don't worry, I finished my MSc and I've been teaching for 4 years now. Okay, so you can calculate my age. And I've been doing a lot of research as well. So that also counts. Now you can add up to all of that and find out my age. Okay, is this clear? Okay. Next is the energy stored in a conductor. How will I do that? So, for energy stored in a conductor, again, let's consider a conductor with a lot of charges. Okay, with a lot of charges. Let's say it's at a distance r. Okay, now it has so many charges. What I'm going to do is I am going to bring more charges. Okay, so the conductor has a lot of positive charges. I am going to bring more positive charges to it. Okay, so if I'm going to bring more positive charge, it obviously has to do work. So I cannot easily bring positive charges. I have to do some work. See, this is a positive charge, this is a positive charge. To bring these two together, I have to do some work. So what will the work be? So the work will be dW is equal to VdQ. Formula for work. Watch part 1 if you don't know this. So now what will I do? I will integrate it. What is V? Q by C times dQ. So from this, dW integral is W. Integral of Q is Q square by 2. So this will be 1 by C Q square by 2. Okay. So work done is 1 by C Q square by 2. Work done is the same as energy. So this is again half Q square by 2. So from this, Q is equal to CV. I know that. So can't I write U to be half CV square? Now, since I know C is equal to Q by V, I can write U to be half QV as well. So I have three formulas for energy, isn't it? Yes. See, this is the first formula for energy. Now, second formula for energy is what? This one. Now, what is the third formula for energy? This one. See? Three formulas for energy. Now, whatever question you get with whatever is given, you can find out. Because I have three formulas for energy. From what did I do here? Very simple stuff. I have a conductor which is fully positive. I want to add more positive charge. So to add more positive charge to my conductor, what I am going to do? I am just going to do some work. What is the formula for work? V dq. I integrated, I get the answer. Very easy. Yes? Okay? Okay. Yes. Next is the redistribution of charges. So, I don't know if I have the time for this. Okay, let's quickly do it. Okay. So, for redistribution of charges, imagine these are two conductors. Okay. I will give problems here. I will do another session for problems alone. Okay. Yeah. Don't worry, NEET. I've got all of this covered. Okay. The only thing that you can do for me is study from my videos and share it with all your friends. Tell them that there's a channel. Let people know. Okay. Tell them there's a channel that's doing a lot of help for first PU, second PUC, KCET, NEET, JEE, whatever. Okay. So, initially these are two conductors. Okay. So, the first conductor, it has a capacitance of C1. The second conductor has a capacitance of C2. Okay. So here, this has a potential of V1 and this has a potential of V2. So C1 will be what? Q1 by V1 and C2 will be Q2 by V2. Now what I'm going to do is, I'm going to join these two conductors with another conductor. So what happens? Charges flow from both. So now, the charges flow until both the conductors have the same potential. Okay. So here Q1 dash will be C1 into V and Q2 dash will be C2 into V. So the charges flow from the first conductor to the second conductor unless and until both the conductors have the same potential. It's like you have hot water and cold water, you pour them together, the particles will run around until all the water has the same temperature. Same thing here, charges will move around these two conductors until both the conductors have the same potential. Okay. Okay. So the common potential, which is V. Okay. So the common potential V is what? It is Q1 plus Q2, the whole divided by C1 plus C2, total charge divided by total capacitance. So V can be written as C1V1 plus C2V2. What is Q1? C1V1. What is Q2? C2V2 divided by C1 plus C2. Okay. Now we also know that charge is transferred. Okay. Now when I attach a conductor to both, a conducting wire to both of these, what happens? Charge is transferred. Yes. So charge is transferred. So change in charge will be Q1 minus Q1 dash. So Q1 is the charge of the first case. In the first case, what was the charge? C1V1 minus, in the second case, C1 into V. Okay. C1V1 minus C1 into V. Now, this is going to be equal to, let's do the math. So, this is going to be equal to C1V1 minus C1 into V. I already found out. Sorry, students. V is how much? I have that. C1V1 plus C2V2, the whole divided by C1 plus C2. Now this is equal to, I'll take C1 outside because it is there in all the terms. I take C1 outside. So what remains? C1 plus C2 across multiplied plus C1V1 plus C2V2, the whole divided by C1 plus C2. Now this is equal to C1, C1. So there is a V1 here. How can I forget that? So C1, V1, C1, V1 I can cancel. Yeah, C1, V1, C1, V1 I can cancel. Now what remains is C1, C2. So if I multiply C1 inside, what does it become? It becomes C1, C2. For both the terms, it becomes that. Divided by C1 plus C2, the whole V1 minus V2. Okay, I want you to do this math in between. You will definitely get it. It's a very easy step. Okay, so now with this, what I will do? I will find out potential energy. Okay, so the initial potential energy is what? It is half C1V1 square plus half C2V2 square. Now the final potential energy is what? Half C1. Finally, what happens? These two conductors, they have a conductor in between. Their potential will remain constant. So it will be half CV square plus half C2V square. Now this is equal to half V square C1 plus C2. Okay? Okay. Now let's do the math. Now here what I'm going to do is, I'm going to take C1 plus C2 outside. So this I'm going to just keep it there. I'll use it later. Okay, you'll understand why I put that there. So here what I'll take is half C1 plus C2. If I take outside, what remains? V square remains. What is V? C1 V1 plus C2 V2, the whole divided by C1 plus C2, the whole square. Okay. Now which is this? Half C1 plus C2 on top. On top. Half C1 plus C2 on top. And then C1 V1 plus C2 V2, the whole square. Okay, I can cancel these. Yeah, I can put it at the bottom. I can cancel C1 plus C2 and C1 plus C2 the whole square. So what remains? So I will get C1 plus C2 here. So I can cancel this square and this. Okay. So students, I am doing this a little fast because I want to finish a little more portion. But I have done all the steps. You can watch it a little slow. You will definitely understand. Okay. After this derivation, we'll go slow. Because this is simply math. That's why I'm just doing the steps here. Okay. Now, if the change in energy, what happens? Initially, you have two conductors. They have some energy. When you put a conductor in between, what happens there? The energy changes. So, if the change in energy, if it is delta U, okay? If the change in energy, let's say it's delta U is basically U initial minus U final. Yes, delta U is U initial minus U final. So, let's substitute the values. So U initial minus U final. U initial is what? It is half C1 V1 square plus half C2 V2 square minus 1 by 2 C1 plus C2 C1 V1 plus C2 V2 square. Now this is going to be equal to, in all the terms, I will take C1 plus C2 as a common term. What remains? C1 V1 square, C1 plus C2 plus C1 V2 square, C1 plus C2 minus C1 V1 plus C2 V2 the whole square. Okay. Now, if you open all these brackets, what will you get? Half C1 plus C2. Inside, I have C1 square V1 square plus C1 C2 V1 square plus C1 C2 V2 square plus this will be C2 V2 both square minus C1 square V1 square minus C2 square V2 square minus 2C1 C2 V1 V2. Oh my god. Yeah. Now what happens? I have to cancel all the common terms. So C1 square, C1 square, C2 V2 square, C1 square. These four terms I'll cancel. So what remains? This is basically delta U. Okay. Delta U. I think all of you are traumatized. Nobody's talking in the chat. Delta U is equal to, what will this be? C1, C2 I can take common. All these three terms have C1, C2. So C1, C2, the whole divided by 2 C1 plus C2. Now you should tell me what's inside the bracket. So from all these three terms, if I take C1, C2 outside, then what I have is V1 square plus V2 square minus 2 V1, V2. What is that? Isn't that V1 minus V2 the whole square? Yes, it's V1 minus V2 the whole square. So now what I have here? What I have here is change in energy is equal to C1 C2 divided by 2C1 plus C2 V1 minus V2 the whole square. Understood? Yes. Sanath has put okay. I'm happy someone has put okay. Okay. So you have another lesson after this class. So let me just ask Pramila ma'am. Okay. Okay. Next, what we're going to learn is the concept of a capacitor. Okay. The concept of a capacitor. So what we discussed till now is what is capacitance, the formula and all of that. So now we're going to start with the concept of a capacitor. So what is basically a capacitor? It has to store charges, as somebody already said. So imagine if this is a capacitor and it's connected to a battery. Okay. If it's connected to the positive, this side will be positive. This side will be negative. Okay. This side will be negative. And there will be an electric field inside the capacitor. Electric field will always flow from the positive to the negative. Okay. So the electric field between the plates. The electric field between the plates E will be sigma by epsilon naught. Okay. This will be sigma by epsilon naught. Now, the potential difference. 1 by C, ma'am, you wrote 1 by 2. Oh, where? It is 1 by 2. It is 1 by 2, no? 1 by 2. Anime fan. It's 1 by 2, right? Okay. Now, potential difference between the plates. Okay. So, potential difference between the plates, V has to be equal to what? The electric field into the distance between the plates. Okay. Let's say here the distance between the plates is D. So, potential difference between the plates is V is equal to E into D. So, it is definitely what? E is what? Sigma by epsilon naught into D. Into D will be epsilon naught okay. So this epsilon naught, I can write it as what? Epsilon naught, I can actually write it as Q by A. How do I do that? Energy derivation. Oh, energy derivation. Where is it? C. Oh, yeah. Our anime fan is paying very close attention to my classes. Very good anime fan. It is C. Superb, superb. Yeah. These mistakes you can make out, no, because I have written the same thing. So even if, if you're watching a live class, you should know it's. Thank you, anime fan, for correcting me second time. So in the first chapter in electrostatics, sigma, which is the charge density, I had written it as Q by A, not I. It is a standard form. It's Q by A. So here I can write this as Q by A epsilon naught. So this here also I can write it as Q by epsilon naught A into D. Okay. So now from this, how will I write my capacitance? So from this, I can say capacitance is what? Capacitance is Q by V. Yeah. Capacitance is Q by V. So this is basically Q divided by Q by epsilon naught A times D. So Q and Q will cancel. This will be epsilon naught A by D. Okay. So this is the basic concept of capacitance. So when you have two charged conductors and they store charge, it is a capacitor. And the value of capacitance is always given by epsilon naught A by D. Now in the same thing, now if I add a dielectric, okay. Now if I add another something, okay, a material, okay. So it is not free, I add a material. Okay. So if I add a material, then what happens? Capacitance will be C dash. Okay. So when it is C dash, this will basically be epsilon A by D. What is epsilon? K into epsilon naught A by D. So this is basically Kc. We already discussed this. Okay. So if you have, instead of vacuum or air between the plates of a conductor, if you have a dielectric, then the capacitance changes. These formulas are very important, students. Even if you are someone who's only preparing for KCET, there are a lot of questions from capacitance. Okay. Now next we will look at the energy stored in a capacitor. For that also you only need formula. So this is half CV square or half Q square by C or half QV. We already discussed this. Okay? Yes. Next we will talk about dielectrics and polarization. So in dielectrics and polarization, you need to know some basics. Okay. So imagine you have a dielectric insulator. Okay. And this has charges moving in random directions. So plus and minus, these have charges moving in random directions. Plus charge, minus charge. When I apply an electric field to this, what happens? When I apply an electric field to this dielectric, you can see that all the charges align in the direction of the electric field. Okay, all the charges that were random, they align in the direction of the electric field. Okay, so the net electric field will now be equal to the electric field that you applied minus the electric field induced. How did that electric field be induced? Because inside what happens now? So inside what happens? All the charges, they go to, the two planes. So this was a dielectric. I applied an electric field. So the electric field that I applied was E naught. Okay. E naught. Now inside, it produces an opposite electric field called E induced. So what happened? There were so many random charges. You applied an electric field. Inside the dielectric, the charges got arranged and they produced an induced electric field. Okay, so that is this induced electric field. So the net electric field is basically the difference between the two. The difference between the applied electric field and the induced electric field. So now if I do it, E naught will be what? E net, I can write it as Q divided by epsilon naught A minus Q induced divided by epsilon naught A. Okay. And E net, I can write it as E naught by Q. No, by K. By K. E naught by K. How did I get E naught by K? I can tell you that also. So E is equal to 1 by 4 pi epsilon naught Q divided by R square. So E dash will be what? 1 by 4 pi epsilon naught K into Q by R square. So electric field initially, then electric field of a dielectric. So basically E dash is what? E by K. So that is what I have used here. Okay. So E naught by K is equal to Qi minus epsilon naught A. Now if you just solve it, you can write E naught by K as Q divided by K epsilon naught A is equal to Q divided by epsilon naught A minus Qi divided by epsilon naught A. Okay. So in all of these, I can remove all the common terms. So what remains? Q by K is equal to Q minus Qi. So Qi will be Q minus Q by K. So Qi will be Q into 1 minus 1 by K. Okay. So this is the induced charge of a dielectric. Okay. All of these formulas, I'll tell you where to apply them and all when we are doing problems. Then you will understand it better. Okay. Next is polar molecules and non-polar molecules. This is a very easy concept. So if you have a molecule where the positive charge and the negative charge are separate, that means they have a dipole moment. The dipole moment always moves from the negative to positive. So they have a dipole moment. They are called as polar molecules. Example, water, chloride, and hydrogen chloride and all that. But a non-polar molecule is where the positive and the negative, they're together. So then there is no dipole moment because they are together. So those are called non-polar dielectrics. Okay? Is that clear? Yes. Okay. Now let's look at the capacitance of a parallel plate capacitor with a dielectric slab. So this is also very important, students. This is also very important. So what we have here, we have a capacitor. Okay. So you can see you have a capacitor. Okay. Inside the capacitor, I have a dielectric. This blue thing that you see, it's a dielectric. Okay. So initially the capacitor has plus, 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 and then minus, 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 minus initially. Okay. Initially it has plus, 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 minus, minus. Now it also has an electric field. Okay. Let's say the electric field is E naught. Electric field always flows from positive. Okay. So electric field is E naught. Now this electric field induces an electric field inside the dielectric. This is what we just saw, an application of what we just saw. So the induced electric field is going to be in the opposite direction. That is going to be inside the dielectric. Okay. So the capacitor plate, it has a electric field E naught. Because we place a dielectric inside the dielectric, it has a field EI. Now let's say the distance, the thickness of the dielectric is T. The distance between the capacitor plates is D. Okay. So now what will we do? What we will do is we will find out the potential difference between the plates. Okay. We will find out the potential difference between the plates. So the potential difference V will be what? It will be the potential difference will be basically the electric field because of the capacitor and the electric field because of the dielectric. So because of the capacitor, what is the electric field? Total electric field is E naught and the distance will be D minus T because T is occupied by the dielectric. So D minus T is occupied by the capacitor. Plus electric field of the dielectric is what? It is basically the net field, isn't it? Electric field of the dielectric is the net field into the thickness of the dielectric, which is T. So one thing you need to remember here is the outer electric field is filled outside and the inside, the total electric field is the electric field of the dielectric. Okay. Okay. Now let's do it. So V is equal to E naught is what? We already know. E naught is Q divided by epsilon naught A. D minus T plus the net electric field is again Q divided by K into epsilon naught A into T. Why K into Q by K? Because there is a dielectric. Now V is equal to Q divided by epsilon naught A D minus T plus T by K. T by K. So the capacitance. So the capacitance of system C is equal to Q by V. We already know. So Q divided by epsilon naught A D minus T plus T by K. So C is equal to epsilon naught A will go to the numerator divided by D minus T plus T by K. So this is the formula for capacitance. Students, this is a very important formula. You can ask your seniors who have prepared for KCET. There are lots of questions using this formula. So you need to know this formula by heart. For your exam, you can't sit and derive this. Okay. S, high S, your Rakshit. Okay, Rakshit from 9th standard. We currently am not doing 9th standard classes, Rakshit. This is 12th standard class. Okay, when you reach 12th standard, if I'm still teaching, I will teach you then. But if you know any 11th standard and 12th standard chetas or chechis or bayas or behens, please send this video to them. Okay, Rakshit. Okay. Yes. So this is the capacitance of a parallel plate capacitor which has a dielectric slab in it. Now we can consider 3 cases for this one. Okay, so we can consider 3 cases. Case 1 is when T is equal to D. Okay, so when T is equal to D, what will this be? C will be K epsilon naught A by D. Yeah. What will case 2 be? Case 2 will be when the dielectric is metallic. When the dielectric is metallic, the constant is approximately equal to infinity. Okay. So the constant is approximately equal to infinity. So then what will you get? You will get C is equal to epsilon naught A by epsilon naught by A, D minus T plus T by epsilon naught, which is epsilon naught A divided by D minus T. Okay. Now if you have a case, you can have a case 3 where you have so many dielectrics. So there what will it be? It will be epsilon by A. The formula will keep on repeating. D minus T1 plus T2 plus T3 plus Tn plus T1 by K1 plus T2 by K1. It will just repeat like that. Okay. Now these are the effect of various, the effect of dielectric on various parameters in a capacitor. Okay. So one thing that you need to remember here is for a capacitor, if it is connected to a battery, the voltage is always same. So this is what you need to remember. If it is connected to a battery, the voltage is always the same, charge is the same, and energy increases. If battery is disconnected, charge same, voltage and energy decreases. Okay. So if battery is connected, what happens? Charge and energy will change. So that I have just proved here using formulas. So when battery is disconnected, what happens? There is no charge flowing. It is just a capacitor by itself, no charge flowing. So what happens? It remains constant. Charge does not flow. Capacitance will increase by K. Potential difference will decrease. Electric field, energy will also decrease. So what I want you to do is, you can just substitute the formulas for each one. Okay. So say for example, potential difference V is equal to Q by C. Okay. So it will decrease. Potential difference will decrease because capacitance will increase. So substitute in each formula and you will get. So same parameters when battery remains connected also I have given. Okay. Now we come on to the last topic of the day, which is series combination and parallel. Very important. So in series, what happens? This is how you have capacitors in series. So this is your battery. Okay. So from the battery, the same charge reaches both the capacitors C1 and C2. So voltage in series is always shared. Okay, all of you should remember that in a series circuit, voltage is shared between all the components. So V is equal to V1 plus V2. What is V? Q by C is equal to Q by C1 plus Q by C2. Q is the same, so 1 by C is equal to 1 by C1 plus 1 by C2. Very easy. The only things you need to remember is, in a series combination, charge is the same, voltage is divided between the components. Now, in a parallel combination, what happens? You have two capacitors and they are connected in parallel. This is the battery. Okay. So, this is C. In parallel combination, C1, C2, voltage does not change, but charge changes. So, charge will be Q1 plus Q2. So, this will be CV is equal to C1V plus C2V. Voltage is the same. In a parallel combination, voltage is not divided. Voltage is the same. So, this will be C is equal to C1 plus C2. Okay. Is this clear? So, with that, we wind up this chapter. Okay. We have to do problems. We have to do problems based on all of this. And I will give you an equation sheet when we are revising for unit test 1. Okay. So from tomorrow onwards, we are going to start with unit test 1 preparation. Okay. So I want all of you to inform all your friends that Vedantu Karnataka is going to start unit 1 preparation. And I want all of you to subscribe and share the video. So if you've liked the class, please let me know in the comments. I would be very happy to hear that. Okay. And also notes, right? Yeah, so many of you are asking notes. I'll share it in the Telegram chat. So please join Vedantu Karnataka on Telegram. I will just share this on Telegram. Okay. Yes. Okay. Thank you so much, students. I love you all. Bye bye. See you all in the next class with another video. Bye bye.